So joining us today is Chris Grenade from Microsoft Quantum Systems Group, and he'll be telling us about how to use Q# for your quantum machine learning needs.
Wonderful. Well, thank you very much for having me here. It's really awesome to be in Toronto for this. So as mentioned, today I'll be talking about what we're doing with the Quantum Development Kit in Q# to empower QML research. So from that perspective, I'd like to jump right into how this fits into what we're doing at Microsoft. Right? Our whole goal with what we're doing at Microsoft Quantum is to empower people to deliver on quantum impact. It's not enough to simply have an advantage. We want that advantage to actually be useful and have bearing on real-world problems. And that's the perspective we take. We want to put the tools in your hands to actually really deliver on that impact. And we know that machine learning offers a wide range of different kinds of impact. And so it gives us a really good place to deliver on that mission, put the tools in your hands you need to do that. So what I'd like to focus on today is how we're doing that. How are we empowering you to go explore QML applications? So the example that I'd like to talk about is the QCC classifier and how you can use Q# with that to explore new ideas now. And by using Q# and the Quantum Development Kit together, that puts you on a good path to start deploying this on the Azure Quantum as that goes into private preview. And by the way, the QCC classifier, I'll mention a little bit more about that later, but is based on joint work. It is another example of real community effort on this, that it's based on joint work, for instance, with Maria here in the room. But so here, for instance, we have some half-moon data that's a little bit of sample data where you might want to try and discriminate between. And when you run through the classifier, you get a fairly complicated decision boundary, but that's able to pick up all but one of the different samples in our validation set. And that decision boundary comes from just actually running things in Q#. You can write it out. This is the actual code that's in the sample that we're writing, where you can say how you want to pre-process the data, how many qubits you want to use to do that, what the learning rate is, and then feed that all into the sequential classifier training to get back out the optimal parameters that you need to go run that model. And so that makes it really easy to see the structure of those ideas as you explore them, right? That you can read them right off of the code. Importantly, we also need to be able to express conventional machine learning ideas. For instance, as you saw, like that, it's not all quantum, right? That we're looking at hybrid computation here. So for instance, you might need to pre-process the data, apply a classical kernel to expand your features. So we can do that in Q# as well. So for instance, here we've got a pre-processor function that we write out by just saying add an offset to each of our features, go and add a product kernel to each of our features. And so we can express that in the same language right alongside the actual QML application. So to kind of take a step back to how this example works, what all had to go in to Q# and the Quantum Development Kit to enable that, to enable us to express those quantum machine learning ideas? Well, first and foremost, the language. Right? We really need to actually be able to have a language that lets us focus on quantum algorithms and quantum concepts. As we build up that language, we need libraries to enable us to do different common subroutines and also to focus on domain-specific areas like quantum machine learning. That needs to be integrated. So for instance, I'll talk a little bit more about this down the road, but Python integration so that it works alongside the tools that you already know and love. Development tools, we know from the history of classical computing that it can be hard to program, without some tools to help out, remind you, oh, hey, this is what that's named, go find where variables are used, where operations are defined. And so we learned that lesson here too and provide enterprise-grade development tools. Last but not least, we really are empowering people because there's a community of people to empower, right? Like this is, the quantum development community has really expanded recently, and it's been really neat to see how that's come back in terms of feedback to us to help us go make a better tool for you, and direct contributions as well. So let's dive into each of those different pieces and see how that enables us to explore. So kind of at a high level, what is Q# itself? It's a language where I can write out different operations and functions and then use a host program to send those across to quantum hardware, such as through Azure Quantum, or run them locally on my machine using a simulator, feed them into a resources estimator. But however, whatever I want to run it on, I take the same Q# program and whatever libraries it references, and I can send it to different machines in that way using my host program. And what's kind of critical to that is that when I write out a program in Q#, what I'm really doing is writing a classical program that sends instructions out to those devices. And then that really motivates that Q# is a domain-specific language for expressing those kinds of side effects. And so that tells us what kinds of features we need in that classical language to help us write out quantum tasks. And in particular, as we do so, we always want to make sure that the focus is on what algorithms and what applications are brought to bear, are being expressed. We want to be able to, it should be a high-level language to let us focus on the structure of those algorithms. So using a few different features in Q#, you can quickly build up those sophisticated algorithms by reusing pieces efficiently. So for instance, one thing that we use all over the place is an idea called partial application that let you hook up different APIs together. And one of my favorite examples of that is if you write out a teleportation operation, just write up, quantum teleportation. So one of the first algorithms you'll generally see when you learn quantum computing, a partial application of a teleportation operation gives me entanglement swapping protocols, because I haven't told it what another qubit looks like hanging around, but I also haven't told it, oh, hey, this is all the qubits there are. I can partially apply a reference qubit to get that higher level algorithm out very quickly. Other features that you see here, when I talk about doing a Bell measurement, I can use the adjoint keyword to say, actually, Bell measurement's the same as Bell preparation, run backward. So use the adjoint keyword to represent running things backward, running the sequence of instructions backwards, so that I can see that structure come out, that I have preparation and then an adjoint of preparation to apply a measurement. I can say what qubits I need using blocks. So for instance, I need the one messenger qubit to perform teleportation, and then if I use entanglement swapping, I need another reference qubit. So I can say what I need, where I need it. And so that keeps, again, the focus on that algorithm. And as I build up more sophisticated things, for instance, I might want to, if I'm writing out a Grover's application, I may want to talk about reflecting about a uniform state. So rather than talking about, say, applying H to everything, and making people, putting the focus back on the assembly language, I can actually give that a name, use features like within apply to say, go do this transformation, then do the reflection, undo that transformation, and I've encapsulated that in something that has a name that I can go document and I can look up and understand as that module. And going further, we've provided a lot of these kinds of modules, a lot of these operations and functions that you can call both in the standard library that kind of get used whenever you're writing a quantum program, and the more specific ones to different domains like chemistry and numerics. And these can all be brought into your Q# applications to add to what you have available there. So when we do so, we use an open statement. So that works a lot like an import statement. In Python, we're using statement in C++ or C#. And then I can just go on and use the different things provided by that library. So for instance, the standard library provides the measurement namespace so that I can do things like measure and reset at the same time as a convenience to just actually, that makes a very short expression of a quantum random number generator. It's literally 3 lines. I use a qubit, I measure and reset in the X basis and return it. And that's because we have that useful measurement routine as an operation in the standard library. These standard libraries, as mentioned, are really designed to help us focus on the algorithm. And so kind of as an example of that, I'd like to step back and think about what iteration looks like in classical programming. Because remember, the view of Q# is that we're writing classical programs that send instructions to a quantum device. So we really need to learn from the history of classical languages. So I might, for instance, write out a for loop, a classical for loop, in terms of indices that range over the length of an array, and then I do something with each of those indices. I might focus on the logical connection between those indices and that array by abstracting that away and just say, I don't care what the indices are, I just want the indices that match that array. I might even go another step forward and have a for each loop that says, hey, do something for each element, I don't even care what its indices are. And then we can also really focus up at the highest level on what the algorithmic structure is to say, apply this operation to everything in that array. And this is, we saw earlier, for instance, if I want to do a Hadamard on everything in register, I can do apply to each H that register. And so it lets us focus on that algorithm rather than thinking in terms of how I implement that algorithm. And this really starts to show its value as we start doing more complicated things, like if I have two different arrays I need to work with at the same time, I can zip them together to focus on how those two arrays are related to each other instead of thinking about index manipulation. I want to think about quantum programming here. I want to think about the actual algorithm rather than necessarily what indices I need to work with. And doing that it gives us another way of expressing kind of common circuit patterns. So, if I take a circuit diagram over here on the right where I do a CNOT between each qubit in two different registers, I can use that idea of zip to relate to arrays and now take CNOT, that built-in library operation, and apply CNOT between each pair, and this focuses on that pattern rather than in a particular expression of that pattern. And you can build up more complicated things, like I can multi-control on one register, all of the CNOT on each element of another register. And I can use these ideas that came from thinking about iteration in a classical sense to build up these kinds of circuit-like patterns, but as programs. And this makes it really easy to think about higher level concepts as well. So for instance, in the numerics library, we provide an idea of an integer and a quantum register so that you don't necessarily have to know how it's represented in that register. You just know that the state of that register is labeled by an integer. And then I can say, reflect about a particular integer, and I can do all the bit banging necessary to turn that into what underlying low-level reflection I want, and then expose that as reflect about this integer. And that makes it really easy to start using ideas out of amplitude amplification and the like to explore as you build up your QML applications. We can bring ideas out of amplitude amplification really easily using this sort of high-level approach. And we can make it even easier by going back to what, as I mentioned earlier, and learning from the history of classical development, that we also just need good tooling. So we've taken the effort to go build out enterprise-grade development tooling. And one important part of that is integrating with good classical languages. We're not trying to reinvent the wheel here. So you can use things like Jupyter Notebook to run your, run your Q# programs. You can write your own host programs in C# or in Python and shuttle your Q# programs across to your target machine. You can also use other languages. Some people have used F#, even VB.NET. So there's a range of different classical languages you can use as a host for your Q# programs. As you go write those, in Visual Studio Code, an open cross-platform text editor and development environment from Microsoft, different code actions can suggest how you might want to improve your code, what else you might, how to fix common errors you might make. So like if I use that mResetZ operation I mentioned earlier, and I forgot to write out the open statement, Visual Studio Code will notice that and remind you, hey, you forgot this. And now I'm not stuck on the kind of the syntactic stuff when I want to think again at that algorithmic level. It helps remind me and get back on track and fix mistakes. Code completion, so as you type out a name, it will remind you what the rest of the name is, give you a brief summary of what that operation or function does. Especially handy, with a lot of these being new quantum concepts, to have that at your fingertips, you know what's available. Many of the samples, samples provided with a quantum development kit can be used without installing anything to help you get right to actually developing in Q#, rather than focusing on, hey, let me go install a bunch of stuff. You can try things using tools like Jupyter Notebook and Binder, launch them online in your browser. And that's partially enabled by using containers. So images for the Quantum Development Kit are available on the Microsoft Container Registry. So if you are writing an application that uses Docker, it's pretty easy to compose that with the Quantum Development Kit to build up new applications that way. And that's also really useful in a research environment, and that can give you a great way to reproduce your software environment, so that when you send a collaborator, send a reader of your paper, hey, here's what software I was using, you can send them a Docker container that way, using the Quantum Development Kit containers. And that kind of functionality has let us do something I find really cool, that the entire IDE, that this is all, the whole Visual Studio Code interface that I was talking about, can now just be used in your browser. So I'd like to go back now to the quantum machine learning example that I talked about with a QCC classifier, and let's just come over here and run it, right? So here's a sample. Using that same sample, that half moon example, and I can just come over here in my browser, go .NET run, and I can see it go train that half moon data, a quantum classifier for that half moon data, and then run it on a validation set. And you can see all the Q# code here. You can hover over, see what each of the different functions and operations do. And that's in the browser using Visual Studio Online. So we've really tried to make it as easy to use, to get involved and get up and running with quantum development that way. So kind of the overarching thought behind all of this is that we're really trying to empower people to go do more using quantum computing, to deliver on the things you care about using quantum computing by putting the right tools in your hands to do so. And I would be remiss if I didn't mention that open source is a huge part of that. We've made the compiler open source, the runtime open source, all of the simulators open source, all of the libraries open source, editor integration. So you can go see how we've done it. You can tell us, hey, here's some feedback as to how you can do it better. And we've really valued contributions on all of the different repos that we have out there that make up the Quantum Development Kit. We've gotten some really neat contributions back on the compiler and runtime, for instance. We just got some neat new libraries features as external contributions that way. And the compiler itself, like, we're getting things like integrating it. We're getting some really neat contributions there. So when I talk about the machine learning library, we're living that, right? That the open source, we're developing that machine learning library and all of the samples for it in the open. So you can go see the state as we're working on it. You can go let us know, hey, actually here's an idea as to how it could be better. You can go try it out now as we're making that library. Let us know what you think. So, with that, I want to close by, putting some links on the screen to help, go further, but go do stuff. It's awesome.
Thank you, Chris. Any questions from the audience?
I'm just curious about the Azure Quantum. How will that look when it's available? Will it be something you compile locally and then you submit jobs to run on hardware via API?
So we're currently taking applications for early adopter status on. So it's not yet in private preview. That'll be coming online. So a lot of the details of that we're still fleshing out and working out. But once that goes into private preview, if you sign up to be an early adopter now at azure.com/quantum, you'll be able to see how that works out. So I apologize, I don't have a great answer at the moment since we're still getting that online.
Any other questions? Yeah? Okay.
Hi. Can I view like this Q# as extended language based on C#?
No, I mean, so the naming sharp there is not to point to C#. Like C# and F# are both things at Microsoft that are entirely different. Like, but more that it's meant to point to a set of tools that all work together. C# and F# are very different from each other, but you can use them together well. And similarly, when we launched Q#, we really wanted it to play well together with the range of different languages we had out there.
So can I like say call C# like in some way in Q#?
So you can definitely go the other way, but the problem with calling into C# from Q# is where the different code is run. So if I think about like having that classical controller in front of a quantum device, right? That might be, if I run it on something like Azure Quantum, right? That's however much latency between you and that machine, and now calling back into C# back on your client, right? So that can be a little bit challenging. We really think of Q# as being the classical program that sends instructions to a quantum device.
So it's like the classical program runs on the, like, say, a pulse generator or whatever that controls the actual quantum device?
I can't speak to the details of any particular hardware setup for that, but it is meant to be the classical thing that actually drives your quantum program. So it's, however that's implemented by partner hardware.